Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about the packed bed tower and the pressure drop related to the packed bed tower. So first of all, what is packed bed tower? This is a packed bed tower. This one is a packed bed tower. In packed bed tower the packing material are present. These are the packing materials. It can be racing ring, it can be plastic, it can be bird saddle, it can be any packing material, it can be ceramic materials. These are the packing materials. In the packed bed tower, the liquid is coming from the top. This is the liquid. It is coming from the top, and the gas is coming from the bottom. This is the gas outlet, and this is the liquid outlet. Here, the gas and liquid contact with each other, and the component transfer from the gas. Here the component from gas transfer from gas to the liquid. Here the component is transferred from gas to the liquid. So the absorption taking place inside this packing tower, and a clean or neatly clean or pure gas is coming out from the top, and a dirty liquid is coming out from the bottom. So this is a packed bed tower, and this is the liquid distributor. This is the liquid distributor to distribute the liquid or the packing material. Now what are the packing material? These are some packing materials. This one is called the racing ring. This one. The B is the metal ball ring, and C is the plastic ball ring. This one. And this D is the bird saddle, and the E is ceramic interlock saddle. Ceramic interlocks. This is ceramic interlock saddle, and this one is the plastic super interlock saddle, and this one is the metal interlock saddle. This one is the metal interlock saddle. So ceramic interlocks saddle, we are usually using racing ring or these saddles. These are the packing material. Now there are two types of pack tower. One is the random pack. Random pack. The pack tower can be used randomly, or it can be structural packing. Structural packing. Packing can be two types. One is a random packing, another is the structure packing. In random packing, the packing material are packed irregularly, like this one, this one, this one, this one. This is a pack tower. This is a pack tower. This is a pack tower. So this is a random packing. For regular, for structural packing, the packing material are arranged in the pack tower regularly, in a regular way. Suppose this. This is called the structural packing. This is the liquid coming out, gas entering, gas coming out. So this is the structural packing, in which the packing material are arranged in a regular pattern, but here there is no regular pattern. So this is the random packing, this is the structural packing. Now what are the characteristics of the packing material? So there are some characteristics of the packing material. Characteristic of the packing material. So there are some characteristics of the packing material. These characteristics are for the random pack tower. The characteristic of dumb tower packing. So for the random pack tower or the random packing tower, this is the characteristic of material for the random packing tower. Like for this tower, which is randomly packed. So the characteristic of this packing material for this packing material in this random packing tower will be given in this table. So these are the packing material: racing ring, ball ring, saddle, interlock saddle, super interlocks, HY pack, and these are the ceramic. These are made from ceramics. Racing ring, the ball ring is made from metal. The plastic, the barrel saddle is made from the ceramic. The interlocks is made from ceramic, metal. These are the size. The racing ring, the size of racing ring is 1 divided by 2, half inch. It can be 1 inch or half inch. This is 1.5 inch. This is the bulk density, which is in lbm per feet cube, 5542. So similarly, this is the total area feet square per cubic feet. These are the total area. This is the porosity. Similarly, this is the packing factor, the pF, and the small Fv and the capital Fv. So this packing factor Fv is called the pressure factor. This Fv is called the pressure factor, and this Fv is the packing factor when there is a mass transfer coefficient is using in our calculation. So when we are using our mass transfer calculation, based on mass transfer coefficient, based on the liquid and gas overall mass transfer coefficient, and liquid gas overall mass transfer coefficient and gas basis, then we will use this Fv factor, and this is for the pressure factor, and these two are called the packing factor. So from this table we also conclude that as the size of the packing material increases, the porosity increases, like this one. The size was half inch, porosity was 0.6. When the size of the rushing ring become 1 inch, then the porosity increased to 0.74. So as the size increases, the porosity increases. Similarly, as the size increases, the packing factor decreases. Similarly, this factor is also decreases as the size of the packing material increases. So as the size of the packing material increases, the density decreases, the total area decreases, and the porosity increases, and the packing factor decreases, and this one is also decreases. From this graph or other you can also calculate. Similarly, this graph shows the relationship between pressure drop and gas mass flux. The Gy is the gas mass flux. Its unit is lbm per feet square into hour, and the pressure drop, unit of pressure drop is inches of water per feet of packing material. And the Gx, the unit of Gx, it is also the mass flux, but the liquid mass flux, Gx, this one is the Gx, like this one. So the unit of Gx is also lbm per feet square into hour, and the packing factor in this, for this example, this is 92. The unit, this is dimension, there is no unit of packing factor, and the column diameter is this data, and this graph is for the those column whose diameter is 30 inch and whose packing height is 10 feet. And this is for the air water system. This graph is for the air water system, and for the random packing tower, which is in which the packing material 1 inch interlock saddle is present. So when 1 inch interlock saddle is present, in this graph will be used. So in this graph, from this graph, this is for the VCs, that is the gas mass flux increases, the pressure drop increases. So this is for the dry tower, this is for the dry tower, this straight line. So this dry tower line shows that as the gas mass flux increases, gas flow rate increases, the pressure drop also increases. And there is a relation, the relation for the pressure drop and the gas mass flux is like gas mass flux is directly proportional to Gy to the power 1.8. So when Gy increases, the pressure drop also increases. Similarly, for the irrigated column, like when the Gx value is 3000, and this is for the Gx 6000, 9000, 12, 15, 20, 25, 30, 36, 36,000. So for example, these are the irrigated column. This blue line shows the irrigated column. So this for the irrigated column. From this figure we also conclude that for the irrigated column the pressure drop is large as compared to the dry column. Suppose this is a dry column, suppose this is 6,600 600 lbm per feet square into hour. For this gas mass flux, the dry packing will give us pressure drop like this 0.16 or 0.17, 0.16 about approximately. Similarly, for the irrigated column at the same GY, the pressure drop will be 0.2. Similarly, if the irrigation is further increased, like for the GX 6000, the pressure drop will further increase, it will be about 0.28. Similarly, if we further increase for the GX 9000, this will be further increase about 0.38. When we further increase, this will be 0.5. When we further increase for GX 15000, it will be about 0.7, 0.73, something like 0.73. So from these graphs we show that as the GX value increases, and when the GY value is constant, then the pressure drop also increases. At fixed GY, when we increase GX, pressure drop will be increases. This one. So for irrigated column, the pressure drop is largest compared to dry column. This is because when water is coming from the top to the fake tower, the void fraction will fill with the water. So when the void fraction is filled with water, then there will be no space for gas to pass through the packing material. So when the space between packing material or the void fraction of packing material is filled with water, then there will be a hurdle for gas to pass through the column. So when the space between packing material is filled with water, like in these cases, then there will be a hurdle for gas to pass through the packing material, and therefore the pressure drop will be increased for the irrigated column as compared to the dry column. In the dry column, there is no water coming from the top. Simply gas is passing from the bottom through the column. So, and this pressure drop is occurring due to the friction losses. When the gas is passing through the packing material, there will be a friction between the gas and the packing material. Due to this friction, the pressure drop will occur. Similarly, when water is coming from the top, there will be a friction between packing material and the tube. So, due to this friction, the pressure drop will occur in the fake tower, which is nothing but delta P, and its unit is inch of water per feet of the packing material. So this was all about the pressure drop and the packing material. Now this is the flooding velocity. This graph shows the flooding velocity. Remember this graph is for the air water system, and when the packing material is 1 inch interlock saddle, and the random pack tower. This graph is for the random pack tower, not for structural packing tower. So similarly, this graph shows the flooding velocity in ceramic interlocks saddle for the air water system. Now this GX value. Similarly, at this point, if we show these points are called the flooding point, because at these points the pressure drop is very high. If we increase the gas mass flux, for example, at this point, if we further increase the gas mass flux, then the pressure drop will sharply increase. Similarly, if we increase, at this point is also called the flooding point. This is called the flooding. These are the flooding points, and at the flooding point, the pressure drop is 2 inch of water per feet of the packing material. So at flooding point, suppose this is a flooding point. So at this point, now if we further increase the gas mass flux G in this direction, then the pressure drop will sharply increases, or sharply increases at these points. So these points are called the flooding points. And for designing purpose, we will avoid flooding in the pack tower. So the optimum gas mass flux will be half of the flooding velocity, or the optimum gas mass flux will be the flooding mass flux. It will be half of the flooding mass flux. So the optimum gas flow rate will be half of the flooding gas mass flux in our designing. So in designing, we will keep the flooding. We will not use the flooding gas mass flux, but we will use the optimum gas mass flux, which will be half of the flooding gas mass flux. So this was the pressure drop. Now this is the simplified form of this above this graph. This is Gx, these are the Gx value, and this is the Gy value. Now this graph is further simplified in this graph, 22.5 graph. So this graph shows, this is for the air water system, interlocks, ceramic interlock saddle, and these are the liquid mass flux, and this is the flooding velocity, which is Gy. Here the Gy is in the x-axis, and this is the Gx. This is Gx, and this was the Gy. Here this is the Gx is on the x-axis, and this is the flooding velocity. This is the Gy. So the flooding velocity, and the unit are lbm per foot square into hour, But here the difference is that these graphs are for the different packing sizes. For example, interlock saddle. This graph is for interlock saddle, but for half-inch interlock saddle material, this graph are obtained. This curve is obtained. For 1-inch interlock saddle, this graph is obtained. Similarly, from 1.5-inch for 2-inch interlock saddle, this one is obtained. So from this graph, we can see that as the liquid mass flux increases, the flooding velocity decreases. Similarly, when the size of the packing material increases, the flooding velocity also increases. For example, if this 5,000 liquid mass flux Gx, and when the packing size is half-inch, then the flooding velocity is something like this one. This is about 700 lbm per foot square into hour. Now if we increase the size of the packing material, then it will be further increased like this one, about 1000. Similarly, if we further increase, it will be nearly 3000. If we further increase, it will be about 2400, or it will be further increased. So as we increase the size of the packing material, the flooding velocity increases. So similarly, when we increase the Gx value, the liquid mass flux, the flooding velocity Gy decreases. Just if we see from this graph, if we increase the Gx value, like the Gx is 300, here is 600, here is 3600. So if we increase the Gx value, like if we increase the Gx value in this direction, here the Gx value is small, here it is large, 36,000, here it is Gx value here is 0, here is 36,000. So when we increase the Gx value, the Gy value decreases in this direction, which is shown in this graph. And for different size material, different graph will be obtained like this type. Now this graph shows, this is the generalized correlation for flooding and pressure drop in packed column. Generalized correlation for flooding and pressure drop. This graph is for the flooding flooding point and pressure drop. So the parameter of the curve is pressure drop in inches of water per feet. So pressure drop in inches of water, delta P in inches of water per feet of the packing material, per feet of the packed height. Per feet means if there is 1 foot of the 1 foot in the height of the packing material is 1 foot, and inches of water. So this is the pressure drop. Now the Gx and the Gy are the mass flux for the liquid and gas. This Gx and this Gy. Gx divided by Gy is for the unit of the Gx and Gy. This is the lbm per foot square into second. Gx and Gy. The unit of Gx and Gy is lbm per foot square into second. Similarly, the density of gas is denoted by rho y. The density of liquid is denoted by rho x. So liquid density of liquid is large. Usually for water it is 1000 kg per cubic meter. For gas it is 1.2 kg per cubic meter, like something like that. So Gx, the unit of Gx is rho x is lbm per foot cube. For liquid and gas, the unit of density is like this. Similarly, this Gy is gas Gy. This is Gc. The unit of Gc is 32.174. So the unit of Gc is 32.174 feet per second square. Feet per second square, lbm divided by lbf. So 32.174 feet per second square into lbm divided by lbf is equal to Gc. Now this is the Gx, this is the rho x minus rho y, this is the rho y, and this is the Pf. This one is the Pf. This is the Pf. This is the packing factor. Its value it can be here is about 92. It can be any value, but here in this graph it is 92. So the packing factor here is 92. Value can be different. So there is a correlation for packing factor and pressure drop. We will also discuss it. But the packing factor is a dimensionless number. Its value is given in the table, in various table. This Ux, the packing factor. This is the packing factor, and this is the Ux. This is the viscosity of the liquid. So the Ux is the viscosity of the liquid, and the unit of viscosity is centipoise. So centipoise, as we know, viscosity is centipoise is 1 poise. So 1 poise is centipoise, like this type of relation. And this is Gy to the power 2 Pf into Ux to the power 0.1 divided by Gc into rho x minus rho y into rho y. This is on the y-axis, and the x-axis Gx divided by Gy into rho y divided by rho x minus rho y under the root. So for various values, these for example, this is, we can obtain the value of this. If we obtain the value of this is 0.2, then we can obtain like 0.025 when the pressure drop is 0.5, and the pressure drop is 0.5, and the value of this x-axis is 0.2, and the value of phi can be obtained from this graph. This is about 0.004. Similarly, when the pressure drop is 0.5, and the value of this Gx divided by dy into rho y divided by rho x minus rho y under the root, when the value of this one is 0.6, and when the pressure drop is 1.5, then what will be the value of this y-axis? That will be simply come to this side. That will be about 0.004, nearly 0.004. So at pressure drop and at this value we can obtain this value. Similarly, at this value or at this value and pressure drop, suppose pressure drop is 0.1 and y-axis is 0.01. So 0.01 pressure drop, 0.01 come to this side, we will obtain this axis, the x-axis value also. So we can obtain various pressure drop from this graph. So similarly, this is also another graph. This is another graph which shows the relation between. This is another graph which is alternate generalized graph, alternate generalized pressure drop correlation. So it is similar to the above graph. Here the Gx divided by Gy into rho y by rho xo. But here it is the capacity factor. This is the Cs. This is Gx divided by Gy, rho y divided by rho x under the root. The unit of Gx dy are same like the above. It is the lbm per feet square into second, lbm per feet square into second, mass flux for liquid, mass flux for gas, and this is the rho y is the, and rho x, this is for the liquid density, gas density. Unit is lbm per feet cube. Unit is lbm per feet cube. This is the pressure drop. This one is the pressure drop. This is the pressure drop. Pressure drop is inches of water per foot of the packing height. So this pressure drop is 1.5, 1, 0.5, 0.25, 0.1, 0.05. Here the pressure, if we see, here the pressure drop is 1.50, 1.50, 0.025, 0.05, 0.1. These are the pressure drop values. Here the pressure drop is also, see the pressure drop. This is the pressure drop. The pressure drop inches of water per feet. And the y-axis Cs, the x-axis is this one. But the y-axis is Cs, PF, packing factor, and kinematic viscosity, packing factor to the power 0.5. and kinematic viscosity to the power 0.05. So kinematic viscosity to the power 0.05. Cs and 2 PF packing factor to the power 0.5 and 2 kinematic viscosity to the power 0.05. So kinematic viscosity to the power 0.05 and 2 packing factor to the power 0.5 and 2 capacity factor. Now what is this capacity factor? This capacity factor is obtained from the superficial velocity and the rho y divided by rho x minus rho y under the rho. The unit of this one is the lbm per feet cube. These two, and the unit of this superficial velocity is feet per second. So this is the capacity factor, and its estimate is also given in the various tables and graphs. So these are the capacity factor. Now this kinematic viscosity, the unit of the kinematic viscosity is the centistork. The unit of this kinematic viscosity is centistork. As we know, the unit of viscosity is torque as the unit of viscosity, and viscosity, the unit of viscosity is like meter square per second. It can be centimeter square per second. Kinematic viscosity is nothing but viscosity divided by density. So the unit of viscosity is kilogram per meter into second. If we divide it by density, then the unit of density is kilogram per cubic meter. So per cubic meter, this meter cancel with this becomes square, and this is a kilogram meter square per second. So the unit of kinematic viscosity is meter square per second or centimeter square per second. So on the y-axis this one is given, and on the x-axis this one is given. So if we know the Gx divided by Gy into rho y divided by rho x under the root, suppose the unit of this x-axis is 0.2, and if the pressure drop is supposed like this one at this pressure drop, and we can obtain the y-intercept, this one which is 0.9. So from these we can obtain the kinematic viscosity. If we are given that this CS and PF is given to us, usually the PF is the also dimension is its unit is its value is 92. It can be 90. It depends on various problems. So suppose if this is not given to us, this 2 is not given to us, but only there are two quantity given to us, delta P, which is 1 inch of water per pit, and if this whole x-axis value is given to us, which is 0.20. So we will come from this graph, we will come through this graph, we will select this point, we will come in upward direction, we will come to this point. So from this we can obtain this y, this values. So we can obtain the x, the y value. Similarly, if the delta P is, suppose if delta P is 0.5, if delta P is 0.5, if delta P is 0.5 and the y-axis is 0.8, then simply come from 0.8 to this 0.5 delta P line and come downward. This is 0.6, 0.6. So which is 0.6, so its value is suppose 0.6. Now if this is given to us, this rho x is given to us, this is given to us, then we can obtain gx from this relationship. So this was all about the pressure drop and other quantity in a plate tower. Thank you very much for your attention.